Hi guys, so this will be your homework for tonight, a little bit different for homework. I want you to watch this video, and this way we can just practice during class tomorrow. This is what I was hoping to be able to get through with tomorrow. So, to begin, we'll start our notes on 6.1, discrete and continuous random variables. So your only homework really is to watch this video and to fill out the note sheet. Come in tomorrow with questions. So, probability distributions. We know that they have to be a probability and counts that go along with them, and we know that the probabilities have to be between 0 and 1 and sum to 1. And so here's the probability distribution we think a lot about. If we toss a coin 3 times. So here are our different options, right? If I were to list them out, we have heads, heads, heads. We have tail, heads, heads. We have heads, tail, heads. We have heads, heads, tails. We have, tails. Let's see what's next. Tails, tails, heads. We have tails, heads, tails. We have heads, tails, tails. And we have tails, tails, tails. I think I got them all. 1, 2, 3, 4, 5, 6, 7, 8. Right? There's 8 different combinations. And so this is what we call the sample space. Right? This is our sample space for our probability. It's all the different possible options. We're now going to let x stand for the number of tails that we get. So you can either have 0 tails, 1 tail, 2 tails, or 3 tails. So let's go ahead and fill out our probability table now. We have the values. You get a 0, a 1, a 2, or 3 number of tails. And now let's think about the probabilities. Well, there's 8 different options. So all these probabilities will be out of 8. Go ahead and fill in how many zeros, 1s, 2s, and 3s. So, 0 tails, that only happens 1 time. That would be this one. 1 tail happens 1, 2, 3 times. 2 tails also happens 3 times. And 3 tails only happens 1 time. So now we have our probability table here. Right? All these numbers are between 0 and 1, and they sum to 1. You can leave them like this or turn them into decimals. That's up to you. So, if I were to create a histogram out of this, right, we have our options of 0, 1, 2, 3. Right? These are discrete probabilities. You can't have 0, or you can't have like 1.5 number of heads, or 1.5 number of tails, or whatever. And so we have, let's go ahead and do the percent tails. Well, we know it's between like 0 or 1 and 8, right? Or you could put it as a probability. So we could do 1/8, right? So we have maybe, and then we have 3/8 is our other one. So we have maybe like 0.375. Here's 0.125. So we have 0. That would be with 1. We got 3 for 1. Oops. For 2, we also had that probability, and for 3, we only have that. This is bad scaling. Bad job, Miss Franklin. Make sure you scale it like using tick marks like 0.1, 0.2, 0.3, 0.4. Really should have done that. 0.1, 0.2, 0.3, and then 0.375. Great. So there's our histogram. They're discrete probabilities. You can only get 0 tails or 1 tail, right? Or 2 tails or 3 tails. You can't have anything in between. We have our probabilities listed on the side, and this is the number of tails. Alright, so our first question, and we're going to think about 2 different methods to answer this. This means, what is the probability that x is greater than 1? So let's interpret that. That means the number of tails is greater or equal to 1. Well, we got a couple options here. We can go ahead and look at our probability table, and we see greater than or equal to 1. Well, I know that's the probability of getting 3, plus the probability of getting 2, plus the probability of getting 1, right? Because that would be greater than or equal to 1 tails would be 1, 2, 3. Right? So we have our probability of getting 3 tails would be 1/8, plus the probability of getting 2 tails, 3/8, plus the probability of getting 1 tails, 3/8. We add those all together. So the probability that x is greater than or equal to 1 is equal to, let's see, 3 plus 3 is 6, 7/8. Again, you could leave it as a fraction, or you can go ahead and change it into a probability, right? You could leave it as 0.875 if you wanted to. Now, another way to do that, I'm going to put that right here. Another way to think about this is if we think about it as, well, the probability that x is greater than or equal to 1, Well, I know that that means 1, 2, 3, getting 1 tail, 2 tails, or 3 tails. It's everything but getting 0 tails. So what if I think of it as its complement? What if I did 1 minus the probability that x is 0 tails? Well, 1 minus 0 tails would be 1 over 8. 1 minus 1 over 8 will leave us with 7/8. So it's just another way of thinking about the probability. Sometimes it's quicker just to add these 3 things up. In other cases, you might want to do 1 minus what it's not, right? Thinking about its complement. These would be all discrete probabilities. Okay? Now, on your back here, we have discrete random variables versus continuous. Discrete we'll start with, and we'll kind of go over that here. And then we'll go to continuous. I'm going to move this over a little bit so you're just looking at this side of that board. Discrete probabilities are discrete random variables, are variables that can only occur in whole numbers or whole increments. So discrete probabilities, you can either be a girl or a boy. You can either have get 0 tails, 1 tail, 2 tails, 3 tails, right? It can't have any of that fluidity in it, right? It's things that are discrete probabilities or discrete random variables. We talked about discrete versus continuous at the beginning of the year. And we know the 2 statements that have to be true about probabilities. The numbers have to be between, all probabilities have to be between 0 and 1. So P has to be between 0 and 1, right, in order to be a probability set. And we also know that the sum of the probabilities have to add to 1. Right, we also know that in order to be a discrete probabilities. So our variables that takes fit sets of possible values with gaps in between. So thinking about our histogram that we just drew, right, it had gaps in between. These pictures will always have gaps in between because you can only have 0 tails or 1 tail. You can't have 1.5 tails or 0.5 tails. So those are discrete probabilities. Discrete probabilities can have expected values that are not whole numbers, but that's something different. So let's go ahead and take a look at our first data. In an experiment on the behavior of young children, each subject is placed in an area with 5 toys. Past experiments have shown that the probability distribution of the number of X toys played with by a randomly selected student is as follows. So this is what they play. They play 0 toys 3% of the time, 1 toy 16% of the time, 2 toys 30% of the time, and so forth. So the first thing what we always do with these probability tables, we make sure that it's a true probability distribution by adding these all up, seeing that they sum to 1, and then also all these numbers need to be between 0 and 1. Check. So we're going to go ahead and we want to figure out, write the event plays with at most 2 toys in terms of X, and what is the probability of this event? So, plays with at most 2 toys. So that means he could play with 0 toys, 1 toy, or 2 toys. 2 toys is the most number of toys he's going to be playing with. So we write that X would have to be less than or equal to 2, implying that the probability is that it could be 0, 1, or 2. So we're thinking about this as the probability of X equals 0, plus the probability that X equals 1, plus the probability that X equals 2. So when we go to add all those 3 probabilities up, we go ahead and we see that we have our 0.03 plus our 0.16 plus our 0.30. And so the probability they play with at most 2 toys is 49%. Another way we could go ahead and think about it is we could say, okay, well that would be everyone besides 3, 4, or 5 toys. So I'll do 1 minus this, this, and this. Another way to think about that probability. The second question is now going to ask, describe the event X is greater than 3 in words. So let's go ahead and do that. I'm going to move back over here. X is greater than 3 in words. So we know that that means that X, well, in this context, X stands for the number of toys they're playing with. So we know that the number of toys played with is greater than 3. So it's greater than 3. It's not including 3 toys, but had to be greater than 3, meaning they had to play with 4, 5, or 4 or 5 number of toys. So we can set that up as X has to be greater than 3 which we know that would be the probability of them playing with 4 toys plus the probability of them playing with 5 toys. When we go ahead and find those two values, we have 4 toys, 0.17, 5 toys, 0.11. We add those two together, we get 0.28. So the probability that the kids played with more than 3 toys is 0.28. Now, our last one is, what is the probability that X is greater than or equal to 3 toys? Well, now that's a little different. That's meaning they could play with 3, 4, or 5 toys. So we're going to add up our 3 probabilities. 1 toy, 2 toys, more than 3 toys, excuse me. So we're saying the probability that they played with 3 toys, 4 toys, and 5 toys. Well, I already know the probability of playing with 3 toys and 5 toys, 4 toys and 5 toys is 0.28. So let's just add it to the probability they play with 3 toys, which is 0.23. We add those two together and we get a probability of 0.51. So notice how important that inequality is, right? This is more than 3 toys, so that would be 4 or 5 toys. Well, this one is 3 or more toys, meaning 3, 4, or 5 toys. So that indication, that probability and sign is really important, that inequality, right? Is it just greater than, just less than, or is it greater than equal to, or greater than, or less than, or equal to? All right, that is different than things that are continuous probabilities. Continuous probabilities are probabilities that, or events that could happen that could have multiple outputs, right? It doesn't just have to be 0, 1, 2, or 3. It could be 1.5, 1.25, 1.3, 1.4, right? All the kind of in-between things. And that happens with normal probability graphs that we're used to seeing, right? These distributions that we've already worked so hard on during Chapter 2. So continuous random variables are random variables that have a series of outputs, right? That you could go ahead and find the probability of these things occurring, but they happen over a series of things, right? There are things that are continuous. So weight. We're weighing Diet Coke cans as they come off the conveyor belt. Do they actually have 12 ounces? Well, they might have 12.01 ounce, or they might have 12.011 ounce, or they might have 11.999 ounces, right? Continuous probabilities. So X takes the value over the interval, and these will all look like our normal probabilities, right? They're all going to have their mean, their standard deviations above and below. Our z-scores are going to come into play again, and our percentiles, right? So we have our 2.5, our 16, our 50, our 84, and our 97.5. So we have our data up here. We're going to have our z-scores. We're going to see those again, and we're going to have our percentiles. So this one, the weight of a 3-year-old female closest follows a normal distribution with a mean of 30.7. So I'm going to put that in here as my mean, and a standard deviation of 3.6. So I'm going to go ahead and sketch out my picture here. We know we have a mean of 30.7 and a standard deviation of 3.6. Notice how this is continuous data. So I'm putting my 2 standard deviations above and below. And it wants us to find out the probability that the randomly selected 3-year-old weighs at least 30 pounds. So we want at least 30, so that would be 30 pounds or more. Well, we could probably take a guess looking at our distribution. It's a little bit below the 50% mark, so it's a little higher than 50%. And we want to know that she weighs at least 30 pounds, so 30 pounds or more. Well, we got to use what we already know. We're going to go from X to Z to percent. We find our Z-score. Z equals 30 minus 30.7 over our standard deviation of 3.6. We get our Z-score of negative 0.1944. Then we use our normal CDF. Z left in this case is negative 0.1944. Z right, 1,000 or something. And you'll end up with the probability that the kid is taller than 30 inches is 0.577. Right? Before we were saying this is the percent, it's also the probability of something happening. So for each problem, I want you to decide, is it continuous or discrete? Right? Is it a continuous random variable, something that happens over a long period of time with a mean and standard deviation, which we'll use a normal distribution to solve for the probability? Or is it discrete, right, that they happen very succinct things? Thanks for watching. Come with questions tomorrow.